did so far. I think the last thing I mentioned was we're gonna start the plane polar coordinates, right? Is that the last thing in the notes? But let's go back a bit and just kind of repeat these steps briefly. So the idea is actually we're coming from the two-body problem. We don't have to, but so if we have two bodies in space, right, they have their positions R1 and R2, and then we can construct the difference vector R1 minus R2. And we can choose the origin to be at the center of mass. Okay. So we did those two steps, and we end up with R1 is equal to M2, I believe. Check me on this. M1 plus M2. And R2 is the one that gets the minus sign. M1 plus M2. So we can express those two original positions in terms of the difference vector, and then we find that mr second derivative is equal to the force between those two. But this mass here is the reduced mass divided by M1 plus M2. Reduced mass. Okay. So we've box down here. So we have a one particle problem. So that's the reduction to a one particle problem of the two body problem. And for the for the rest of the time, or for a while at least, we just treat this formally as a one body problem and don't worry about there being two bodies at all. Okay. It stands on its own. Okay. So what came then was, because it's a central force, it has this form here. It's a function of the separation distance times this unit vector. So that's what it means to be a central force, as opposed to just any old force. A central force directed along the line that that connects these two particles. And what's the next step? The next step is that you have a potential energy function for a central force. It means energy is conserved. So the way to show that is you can get a potential energy function that's only a function of the separation distance, that radial distance, because if you do an integral like this, or the work integral to a minus sign, you have this unit vector, and this unit vector dotted into dr is just going to be equal to equals dr. Okay. And that means it's only that radial component that plays a role. Think of this dr here as being an arbitrary infinitesimal. It has, you can decompose it just the way we did in plane polar coordinates. We would have a dr component, a radial, and a d phi component, and they would be perpendicular in match. So this is why you have this. So you have u, which would have been a function of vector r, is actually just a function of the scalar r. And if you, so yeah, let's actually one more step here. R, and we can say we've got f of r prime, r prime, some arbitrary initial point. this expression here. What we're going to get is by fundamental thermocalculus, essentially. We can get minus the integrand evaluated at the upper boundary. You guys know that theorem? Have I demonstrated it for you guys before? Just accept it. Maybe, we'll do the proof of that sometime soon. Okay. So anyway, that is back to derivative here. It's f of r, upper bound. And then the gradient, the chain rule tells us the gradient of r, which is r over r. The thing is, we're about to do this, or we're doing this in math methods, but it's worth doing more than once, okay? So you have energy is conserved. Is conserved. And in fact, I'm going to do the energy conservation in another step as well. Okay, so I'm going to owe you guys this this proof. It's an interesting one. I keep using it. I've used it a couple times. But yeah, we'll move on. So energy being conserved now follows the same pattern it did for one dimension that we had a while ago. So we're going to leave this up here. So energy, and you would say we've got 1/2 mv squared plus u equals e, right? That's how we learn it. What this is 1/2 m r dot product with itself plus u of r equals e. And we'll leave it there in the sense of the vector for the moment. The conservation law tells us that we have to take the time derivative and see that it's equal to 0. So equals 0. So that's what we actually have to prove. The time derivative is equal to 0, and this is 1/2 m 2 r dot our second derivative, chain rule, plus this would be, let's do this, du dr dotted into dr dt. We're going to practice all of these. I may in fact just assign these. We'll just take them as the symbolic version first. Your 2's cancel. You can factor out r dot, and you end up with r second derivative plus du dr vector equals 0, and that's Newton's law, because that's negative f. So r dot of r's second derivative minus f equals 0. Okay. So this is equal 0 by Newton's law. Okay. So yeah, there's a couple technical steps we should practice, even on this proof right here. I don't want to interrupt this too much, but we will. In fact, I'll assign these. These are good for you guys to work through. And the way I'll assign these is that, first of all, we have to know, when I say du partial u over r vector, what I actually mean is the gradient of u of r, okay? And this dot product comes from the chain rule, from the multivariable chain rule. So if we were to write this thing out, I'll call this homework. So this equation star written out in more detail is gonna be 1/2 m x dot squared plus y dot squared plus z dot squared. You guys see that? You know, as a dot, square of a vector is a dot product with itself, right? And it's a velocity vector, so that's the first thing to make sure. And then we would have u of x, y, and z equals e. So that's the first step. Okay? Now if you take the complete time derivative, so this is homework, so you write that out, and then next, complete time derivative of this thing. Does it really equal 0? And you take the complete time derivative of this, and you see you have a chain rule, right? 2x dot x double dot and so forth. And so what you'll see is that this complete time derivative explicitly taken is supposed to give you this. And what about the complete time derivative of u of x, y, and z? This is where you have to remember your chain rule, your multivariable chain rule, because that would be du dx, dx dt. If it were only a function of one variable, it'd be done, right? But the way these work is that you just sum them. I'm going to give you guys the proof of that in math methods later on. It actually goes back to linear algebra. It's the y. So yeah, you go through with that, and you come up with this, and the other homework-worthy problem, just to practice, and that refers to what we just had on the board, is if you have gradient of r, what is that? That's d dx of root x squared plus y squared plus z squared plus d over, oh, sorry. And very important not to mess this up. I hat, right? Okay. Sometimes people leave the unit vectors out. I'll just put this underneath here, plus dy. Because remember, that's what this magnitude of r is. Plus d squared. J hat. K hat. So we do this in the very explicit, tedious form because this has a shorthand that after you've done this several times, you can just knock out the way you have other differentiation rules in your repertoire at this point. Okay. So, and what you're going to find is that's that unit vector. So go ahead and do this calculation carefully and make sure you see it. And this one and this here will bring you up to date with the stuff I've demonstrated so far, right? So all the claims I've made about central force so far will be brought up to date if you just make sure you run through these. Good. So where does that put us? Oh yes. So that puts us in conservation of energy land, which we now know we have conservation of energy in the central force problem. Yes. You know, I'm going to show you right now, while we're on these math topics, I'll show you the proof of that fundamental theorem type of expression. Okay if I erase these? You guys have that okay? Because this gets used quite a bit. practice these and be caught up, so to speak, in what we're doing. So what we're looking at is this, suppose you have d over dx integral f of, I can use any integration variable s ds a to x, okay? So this kind of expression comes up often enough, and what the derivative is of this integral with the argument up here at the upper bound is just the integrand evaluated at the upper bound. A related proof would show that if it were the integral, if the x were at the lower bound, then you would get a minus sign in there. But you guys can play around with that yourself. So what we have here is the following: d over dx, I'll just rewrite this as ds. We just take the definition, it's the limit as h goes to 0 of the 1 over h. So I'm just going to plug in the definition of the derivative. Okay. So 1 over h integral a to x plus h f of s ds minus integral a to x f of s ds. Limit h goes to 0, f of x plus h minus f of x over h, right? You guys are familiar with that. So what you have here is by this additive property of the integral, this is a to x plus h, this is a to x only. So, if we had a x plus h, then the difference of these two is right there. The difference of those two integrals, so that is integral x to x plus h f of s ds. Okay. And then since we're making h small, we can use some kind of intermediate value there. But there's an intermediate point here at which equals limit h goes to 0, 1 over h f of c times h, right? There's some point in here between x and x plus h, so x less than or equal to c less than or equal to x plus h. Right? There's a point at which that integral is equal to this width times the height at that point. That's something you guys saw when you first learned calculus, right? And then these cancel, and as h goes to 0, this turns into f of x. So yeah, I've used this a couple times this semester already. I'm sure I'll use it a few more times as well. So yeah, that was a basic proof, good one to keep in mind. Keep that one in your arsenal, so to speak. There are interesting, like I said, there are interesting corollaries to this. If you integrate from, x, if you have the x as your lower bound, you get a minus sign. If you have two functions, for example, I'll put this as a note, maybe we should prove this as well. If you had d over dx integral f of s ds, say phi1 of x, phi2 of x, you'd end up with f of phi2 of x, phi2 prime of x minus f of phi1 of x, phi1 prime of x. And you could do that, you could do this as well. Hold on to this maybe if I don't have enough homework ideas, I'll have you guys prove this one. But the proof just goes along the lines of what I just did. So anyway, Good, so we have that. So now we're back to the central force. We got this all races. Good. Now we're back to the central force. And we have conservation of energy. We want to just pull together everything we have at some point. So next though, I'm going to write it all back on the board. So next we had angular momentum. And there R cross P, and in our case, R cross M, R dot, we can use those. And we showed that dl dt was equal to 0. So I showed you that proof. It had to do with the fact that it is a central force. Well, let's do it anyway. We're doing all these things. dl dt equals r dot cross mr dot plus r cross mr. Second derivative, just by product rule. And this is 0 because r dot cross product with itself is 0. And this is 0 because we've got r cross f of r over r. So for the same reason, right? These are parallel. So this is equal to 0, and L is equal to constant. And now we have the argument that because L R cross mr dot, because that's constant, these two vectors lie in a plane, any two vectors lie in a plane, their cross product is perpendicular to that plane. That means R and R dot are always restricted to a plane. Position and velocity are restricted to a plane, that means the motion is restricted to a plane. So motion is restricted to a plane. Good. So now we've reviewed all that stuff. It's fine. We got a little extra insight on the way. Good. Yeah. Therefore, we are going to use plane polar coordinates. Plane polar coordinates. So motions in a plane, we're using plane polar coordinates. We have R, and we've studied these for just this reason. V is equal to R dot R hat plus R V dot V hat. So now we get one of the first applications of this. Okay, so, and L is equal to, so we've got R cross mr dot, so we have R hat cross product M R dot R hat plus R dot V hat. Okay, let's write this down. You want to see where this is going? Remember, these R hat and phi hat seem kind of absurd, right? They're moving around, but they're unit vectors and they are orthogonal vectors. So the cross product of R hat and R hat is going to vanish. The cross product of R hat and phi hat, let's make a little decision here. So XY plane, we would have an R hat and a phi hat. What would the cross perpendicular to there, we're actually not gonna have to use it, but, you know, we have to be aware of it. So let's go ahead and write this out. We've got, I'll go ahead and write the whole thing out. We've got M, R dot, R hat, cross R hat, that's the one that's gonna vanish, plus M, R, so I'm doing this one, it's M, R squared V dot R hat cross V hat. This one vanishes, and this one is M, R squared V dot K hat if you want. Right? Main thing we have is that, yeah, constant, but okay, we're restricted to the plane, but if we include the third dimension, we got M, R squared V dot K hat. Good. But, so let's go ahead and write this. So L is M R squared V dot K hat. And the magnitude of L is just M R squared V dot. What else do we have to say? Well, if it's gonna be the magnitude, then we would have to have a magnitude of phi dot, which could be positive or negative, but we'll just leave it like this. So then it can actually have a sign. That won't give rise to any ambiguities, because when we put this into expressions where the magnitude plays a role, it'll always come in squared. It'll always be squared. Good. So there's our angular momentum in plane polar coordinates. Okay. You know, I think let's look at the, we can do the energy. Yeah. Finally, energy, and then we'll return to something here. Finally, energy, we have 1/2 M R dot squared plus U of R is equal to E. We'll go ahead and use these things, so we'll have 1/2 M. Now this R dot squared, oh, I forgot to put the dot here. Yes. Fix that, R dot. So R dot squared, we're gonna write this out, R dot R hat plus R V dot V hat. Dotted into itself, R dot R hat, V dot V hat. And then we've got the U of R equals E. And now again, the fact that these are unit vectors and they're orthogonal, we just end up with 1/2 M. We get an R dot squared, R hat into itself, then the R dot R hat into R phi dot phi hat vanishes. R dot R hat into R phi dot phi hat. So the R hat phi hat always vanishes. The only one that's left is R phi dot and R phi dot, so plus R squared phi dot squared plus U of R is equal to E. So good, we got conserved angular momentum, conserved energy. It's the fact that we have conservation laws that allows us to solve the dynamic problems. So F M R dot squared, R squared, P dot squared plus U of R is equal to E.
Where did we get R squared from?
Here. So we had R phi dot phi hat and dot product with R phi dot phi hat.
Oh, there's another R, okay.
Yeah. R phi dot phi hat. And like I said, the cross terms vanish. You do the same thing with the spherical polar coordinates, but we stopped. Well, actually, did we do that with spherical polars? We may have already done the V squared. Okay, the same thing with spherical poles. I'll have to check whether we did that or not. Okay, good, so two conservation laws. These are coupled differential equations. These are first order differential equations, because that's first order, that's first order, that's first order. So two coupled first order differential equations for the central force problem. Let's go back to our original differential equations, see if we can remember what they were. Okay, good, so there's a result. Hold on to. Yeah, we'll do this all several times, it'll become, so the differential equations in plane polar coordinates what were they again? They were m r double dot minus r v dot squared equals f of r. And we had m 2 r dot v dot plus r v double dot equals, let's call this, actually, let's call this f sub r, and let's call this f sub v. Okay. We looked at these when we were talking about the pendulum, at that pendulum moment problem. So the thing about, so this is very general, differential equation, plane polar coordinates, but what about central force? For a central force, we say this is F of R, right? And what do we say about this one for a central force? Pop quiz, what do we say about the F sub phi, phi component? When there's a central force. We know exactly what it's equal to at the end. Anybody? Central force. Remember, central force means F is directed along the center, line from the center. So that means this one is actually equal to 0 when we have a central force. So we only have the radial force, we don't have that tangential force when there's central force. So what this means though, is that this should actually be a complete time derivative, okay? And in fact it is. So d over dt of m r dot squared v dot, which is what we have, no, not r dot squared, mr squared v dot, is equal to m, so the complete time derivative, m 2r r dot v dot plus m r squared v double dot is equal to r times, do I have to factor out the m? Yes, I'll factor out the r and the m. So rm times 2 r dot v dot plus r v double dot, right? So that's just applying the chain rule to this expression, and then what I find is that this is 0 when I have a central force. So this is just an alternate discussion, derivation of the conservation of angular momentum. Okay. So the conservation of angular momentum is equivalent to not having that tangential component. Okay. So conservation of angular momentum. necessarily have to solve these anymore. They come in handy, as we saw already on the pendulum and other problems like that. But when it comes to the central force, we're actually going to continue with this expression, with these two expressions here, because they are already first order. If you start with these, you have to go from second order to first order. And one place you do that is here, right? By having a central force, conservation of angular momentum conserved, then you actually have the first integral of the motion, namely this is constant mr squared v dot. But then you still don't have this one. Okay? So to get from second derivative down to first derivative, you need some other piece of information, and that's already obtained right here. So that's what we're going to do next. We're going to write down the energy and see what we can do with these two conserved quantities. This here was just to make contact with the other stuff we've been doing. So let's just rewrite these. So we're now motion restricted to the plane, central force, L and E are conserved. So now we'll just write conservation of energy and angular momentum. We'll write these down again and see what we can do. Okay. So we'll have L m r squared v dot. In fact, I'm going to write it in the other order just for optics. So m r squared v dot, this is our one conserved quantity, and 1/2 m r dot squared plus u equals e. I'll write u of r there. So those are our two conserved quantities. And the way we tackle this is to take the phi dot and solve so that we get L over mr squared. And if we plug this expression right into here, we now have one differential equation, one first order differential equation. So that can now be solved. So we're going to plug this into the energy, and we'll have 1/2 m r dot squared plus 1/2 m r squared, and then square phi dot, and just like I said, we're going to get the L as an L squared, m squared r to the fourth plus u of r equals e. And then we'll put this in the form that we're going to always study it in, just simplifying 1/2 m r dot squared plus L squared. See, m squared, we're going to have 2m r squared over r to the fourth, so 2m r squared, L squared over 2m r squared plus u of r equals e. So this came from the kinetic energy, right? This piece came from the kinetic energy because it was right here, and we did that substitution. Notwithstanding that fact, we're going to call this combination the effective potential. Effective potential. This is a really standard move. I know at first this often leads to a little confusion because it came from the kinetic energy, it's part of the kinetic energy. The reason we call it the effective potential is because the formal problem now looks like this. It is effectively a one-dimensional problem. we can apply all of our one-dimensional skills to this expression here, and it looks completely standard, right? This is, but yeah, this is only part of the kinetic energy, but as a one-dimensional problem, we can just analyze it, and what we have here, we've got a one-dimensional problem, so one-dimensional motion, so to speak, with, with the U of R and R greater than 0. That's basically, or I can say R greater than or equal to 0. So when we did one-dimensional motion, we often had, x goes from minus infinity to plus infinity. Here, we have R positive, but other than that, it's the same.
But if it's 0, we get like divided by 0.
That's right. But if L is equal to 0, which is possible, you can have the 0 in there. But you're right. If you're doing a two-body problem, for instance, you don't have that. Let's just put that. I'll leave the R greater than or equal to 0, and note that if L is not equal to 0, then we have to restrict R greater than 0. Yeah. That's a good point here. Let's see what else we can do in the last couple of minutes. So effective potential, effectively a one-dimensional problem. So you then solve this problem, and then you go back and remind yourselves, oh yeah, but we're actually working in two space. So I'll just even give it a kind of the prototypical example of an effective potential. Here's the thing. Suppose you had a one-dimensional problem, and it looks like this. Apply all your skills. You can say, well, here there's an equilibrium point. It's a stable equilibrium point. And you can say, if I have slightly greater energy, then I have oscillations around that equilibrium point and so forth. So all of those things that we've studied and learned how to do, we can apply to this. Okay? But yeah, suppose you do have a stable equilibrium point in the effective potential. But it really was and is a two-dimensional central force problem. What kind of motion is that? If R naught, you've got E0, you've got R0, and you're saying, particles just resting there. What's it doing in the original problem?
Keeps like the same orbit.
Yeah, it's an orbit with a constant radius. And then you could go back to here and say, oh yeah, well L was conserved, and let's let it be non-zero. If L is 0, then you really are just sitting here, and that's the end of the story, right? But if L is non-zero, you've got a constant, you've got an R0 that's constant, therefore phi dot is constant, which means you have uniform circular motion. So I'll just end it right here with example, perfect place to stop. If E equals E0, and now I'm talking about my picture here, R equals R0 equals constant, then we go back to that M R naught squared P dot equals L, and because those are all constants, R naught and L, therefore P dot equals constant, and therefore we have uniform circular motion. So that's a completely solved problem, you could say. Uniform circular motion. Good, and that's all we've got for today. That's perfect. We'll leave it at that. they gotta come up with a couple more homework problems too, but we have a couple on our list.